Right, we are looking at different ways in which we can optimize the paging process by cutting down on the number of comparisons you have to do with the page table. So the last thing we looked at was hierarchical paging, where you have a page table for a page table. So by making minor tweaks to the idea, what we do is we come up with this thing called hashed paging or hashed page table. So again, the objective is the core essence of paging remains the same, but what I want to do is, instead of making a linear sequential check on my page table, I want to optimize in some way. So what happens is we have a hash function. So again, I will proceed assuming that you are aware of the hash ADT and hash functions from your data structures course, because if I set out to explain hash, that will take another entire segment of its own, and that is not part of the scope of this course. So in case you're not familiar with what the hash ADT is and how it works, please pause this segment and brush up your basic knowledge of hash, and please come back. So yeah, assuming you all are familiar with what a hash table is and what a hash function is, let's look at hashed paging. So what happens is, again, your CPU has a logical address. Again, the logical address has page number, page offset. Again, the offset goes directly as such. Page number to frame number transformation is where we are trying to do some tweaking. So take the page number, you pass it through the hash function, and you decide which bucket of this hash table it belongs to. So within that bucket, you will have a few values of page number, frame number, page number, frame number. So within that you will compare. So what this hash table is like your page table, but what happens is, in your page table you had all the entries: page number, frame number, page number, frame number, page number, frame number, so on. So instead what you do is, you create some buckets in this hash table, and in each bucket you put some entries: page number, frame number, page number, frame number, so on. So a classic example is, if you come across hash in your data structures course, the example most likely would have been taught is using modulus of the array size. If let's say your hash table size is 10, then your page number modulus 10 is a classic example of a hash function. So any page number that ends with 1 will go in the first bucket, anything that ends with 2 will go in the second bucket, anything that ends with 9 will go to the 9th bucket, and anything that ends with 0 will go to the 10th bucket. So if I have a page number 14736, it will be in bucket number 6. That's the logic. So based on that idea, you construct a hash table, and in every bucket you fill the corresponding page number, frame number, page number, frame number details. So this is one bucket. Inside that, Q is a page number, S is the corresponding frame number. Then you have a pointer to the next. Again, P is another frame number, R is the corresponding frame number. Then you have a pointer to the next entry, and so on. This is a linked list. So now when a page number comes to you from the logical address, you apply the hash function to see which bucket it falls under. You go to that bucket, and only for those elements you're going to do a linear traversal until you find the match. So here R happens to be the frame number corresponding to P, so you take R. Your frame number is ready, you already have your offset, you will go and access your memory. So again, it's very straightforward. It's just instead of checking everything, you are dividing it, let's say, into 10 buckets, so your number of comparisons comes down by 1/10. That's the idea of hashed paging.